Artificial intelligence did not emerge suddenly or mysteriously. It developed from earlier efforts to automate reasoning and calculation. This video explores how AI began as a scientific idea, tracing its roots from early automation through symbolic reasoning to the first formal definitions of artificial intelligence as a research field. Understanding AI's origins provides essential context for modern systems. Many current debates about AI capabilities, limits, and risks echo questions first raised decades ago. By examining early assumptions and methods, we gain insight into why certain approaches succeeded, why others failed, and how historical lessons still shape AI development today. Long before computers, humans sought to automate tasks. Early automation focused on mechanical repetition rather than intelligence. Devices were built to follow fixed procedures, not to reason or adapt. These efforts laid conceptual groundwork, but did not yet involve what we would recognize as artificial intelligence. Examples of early mechanical automation include clocks, looms, and calculating machines. These devices followed predefined physical rules to produce consistent outcomes. While impressive for their time, they lacked flexibility and decision-making. Their behavior was entirely determined by design, not by learning or reasoning. The key distinction between automation and intelligence lies in adaptability. Automation repeats predefined actions, while intelligence involves reasoning under uncertainty and choosing among alternatives. Early machines could execute instructions, but they could not evaluate situations or modify behavior based on abstract goals or concepts. The foundations of artificial intelligence emerged from mathematics and logic. Researchers studied formal reasoning, symbolic representation, and proof systems. These disciplines suggested that reasoning itself might be expressed as manipulation of symbols according to rules, opening the possibility that machines could perform intellectual tasks. Slide 7. Early computing theory introduced key ideas such as algorithms and computation. An algorithm is a step-by-step procedure for solving a problem. If reasoning could be reduced to algorithms, then machines might be able to perform reasoning mechanically. This idea became central to early AI research. Alan Turing played a foundational role in this shift. He explored what it means for a machine to compute, and whether computation could capture intelligent behavior. His work did not claim machines were intelligent, but it provided a formal framework for thinking about machine-based reasoning. The Turing machine was an abstract model of computation. It showed that complex processes could be built from simple symbolic operations applied repeatedly. This abstraction demonstrated that any computable process could, in principle, be performed by a machine following formal rules. Turing also posed a famous question: can machines think? Rather than defining thinking philosophically, he reframed the issue operationally. The question became whether machine behavior could be indistinguishable from human behavior in certain contexts, shifting focus from inner experience to observable performance. The Turing test proposed evaluating intelligence through conversation. If a machine could convincingly imitate human responses, it might be considered intelligent by this criterion. While influential, the test measures behavior, not understanding, and remains a limited tool rather than a full definition of intelligence. After World War II, rapid advances in computing accelerated interest in machine intelligence. Wartime research had produced electronic computers capable of complex calculations. Researchers began to ask whether these machines could go beyond arithmetic and perform tasks associated with reasoning and problem-solving. Early digital computers, such as ENIAC, demonstrated the feasibility of large-scale computation. The stored program concept allowed machines to manipulate instructions as data. This flexibility suggested that computers could potentially reason about symbols, not just numbers. Researchers soon shifted from pure calculation to reasoning tasks. Instead of computing numerical results, machines were asked to solve puzzles, prove theorems, or plan actions. This marked a conceptual leap from numerical automation to symbolic problem-solving. Symbolic AI emerged from the idea that intelligence consists of manipulating symbols according to rules. Symbols represented objects, relationships, or concepts, and reasoning was modeled as rule-based transformation of these symbols. Intelligence was seen as a form of formal symbol processing. In symbolic AI, meaning was defined externally by humans. Symbols had no inherent understanding for the machine. Their interpretation came from designers. This allowed precise control, but required that all relevant knowledge be explicitly encoded, a requirement that would later prove limiting. Logic became the primary tool for early AI. Researchers used propositional and predicate logic to represent facts and rules. Reasoning was treated as logical inference, where conclusions followed formally from premises. This approach emphasized clarity and mathematical rigor. Problem-solving was modeled as search through a space of possibilities. The system explored different states, applied rules, and moved toward a goal. This framing allowed general problem-solving strategies but struggled with complexity as problem spaces grew large. The logic theorist, developed in the 1950s, is often considered the first AI program. It successfully proved mathematical theorems by mimicking human reasoning strategies. This achievement demonstrated that machines could perform tasks once thought to require human intelligence. The general problem solver aimed to solve any problem given an appropriate formal description. It represented an ambitious attempt at universal intelligence. However, it worked best on simplified problems and struggled with real-world complexity, revealing early limits of general symbolic approaches. Rule-based systems became central to early AI. These systems used explicit if-then rules to determine behavior. Knowledge was encoded manually by experts, and the system applied rules deterministically to reach conclusions or actions. In rule-based systems, knowledge took the form of explicit statements about the world. This made reasoning transparent and explainable. Designers could trace decisions step by step, an advantage still valued in certain applications today. Early expert systems applied rule-based reasoning to specialized domains such as medical diagnosis and engineering. These systems performed well in narrow, controlled settings, reinforcing optimism about AI's potential to replicate expert-level reasoning. Rule-based AI offered clear strengths: predictability, interpretability, and control. Outputs followed directly from encoded rules, making behavior understandable. These systems were reliable within their designed scope, provided conditions remained stable. However, rule-based systems were brittle. Small changes in conditions could cause failures. As rules multiplied, interactions became difficult to manage. This combinatorial explosion made scaling complex systems impractical. A major challenge was the knowledge engineering bottleneck. Encoding expert knowledge manually required significant time and effort. Capturing all relevant exceptions and nuances proved nearly impossible, limiting system coverage and adaptability. Early AI research was marked by strong optimism. Many researchers believed human-level intelligence was close. Predictions were bold and expectations high. This optimism attracted funding, but also set the stage for disappointment when progress slowed. The term artificial intelligence was formally introduced at the Dartmouth Workshop in 1956. Researchers proposed studying intelligence as a computational phenomenon, establishing AI as a distinct academic field with ambitious goals. The Dartmouth Conference brought together key figures who believed that aspects of intelligence could be precisely described and simulated. Their vision framed intelligence as computation and inspired decades of research, even as specific methods evolved. Early definitions of AI focused on machines performing tasks requiring intelligence if done by humans. This task-based framing emphasized observable capability rather than internal experience, shaping how AI progress would be measured. AI developed as an interdisciplinary field, drawing from computer science, mathematics, psychology, linguistics, and philosophy. This diversity enriched the field, but also created differing assumptions about what intelligence is and how it should be modeled. Early research goals included natural language understanding, vision, and reasoning. These goals remain relevant today, though methods have changed. Early successes often involved simplified environments that did not reflect real-world complexity. Government and institutional funding supported early AI research, particularly during the Cold War. Interest was driven by potential applications in defense, planning, and automation, reinforcing high expectations for rapid progress. Initial demonstrations showed promising results in controlled settings. Programs solved puzzles, played games, and manipulated symbols effectively. However, these successes did not generalize easily beyond narrow problem domains. A gap emerged between laboratory success and real-world performance. Real environments are noisy, ambiguous, and unpredictable. Symbolic systems struggled to handle uncertainty, incomplete information, and continuous change. When progress slowed and expectations were not met, funding declined. These periods became known as AI winters. They reflected not failure of the field, but overconfidence in early assumptions about intelligence and complexity. Important lessons emerge from early AI. Intelligence is harder than expected, and hand-coded logic does not scale easily. Real-world reasoning requires dealing with uncertainty, data variability, and incomplete models. Despite limitations, symbolic AI left a lasting legacy. Logical reasoning, planning, and knowledge representation remain important components of many systems. These ideas continue to influence modern hybrid and rule-based approaches. Modern AI still uses symbolic elements in planning systems, expert rules, and knowledge graphs. While data-driven learning dominates many applications, symbolic methods provide structure, constraints, and interpretability. Studying AI history helps avoid repeating mistakes. Understanding why certain approaches struggled informs better system design and more realistic expectations. History provides context that tempers hype and supports responsible progress. A common misconception is that early AI failed completely. In reality, it achieved important insights and tools. The issue was not uselessness, but mismatch between ambition and feasibility at the time. Early AI succeeded in formalizing reasoning and demonstrating that some intellectual tasks are computable. These contributions shaped computer science and clarified which aspects of intelligence are easier or harder to automate. Early AI also underestimated complexity. Researchers assumed that once logic was formalized, scaling would be straightforward. Real-world intelligence turned out to require far more context, data, and adaptability. These limitations motivated a shift toward learning-based methods. Instead of encoding rules manually, systems would learn patterns from data. This transition marked the beginning of machine learning as a dominant paradigm. The shift to learning did not erase symbolic ideas. Many modern systems combine learning with structured reasoning. AI progress is cumulative, not a sequence of discarded paradigms. Defining intelligence remains an open question. No single definition captures all aspects. Early AI framed intelligence computationally, a perspective that remains influential but incomplete. The core takeaway is that AI began as an attempt to formalize reasoning using computation. It was grounded in logic and mathematics, not mysticism. Understanding this origin clarifies both AI's power and its limits. AI progress has been non-linear, shaped by cycles of optimism and recalibration. Advances build on earlier work, even when methods change. Historical awareness supports more measured expectations. Modern AI inherits both strengths and weaknesses from its origins. Appreciating this continuity helps practitioners and policymakers engage with AI more realistically and responsibly. Next, we examine how AI evolved from symbolic systems toward data-driven learning, setting the stage for machine learning and modern AI techniques used today. The expert systems era represents one of the first periods when artificial intelligence moved from academic experiments into real-world applications. This video examines what expert systems were, why they achieved early success, and why their limitations eventually became clear. Understanding this era explains both early optimism and later caution around AI deployment. Expert systems were a class of AI designed to replicate the decision-making ability of human experts in narrow domains. Rather than learning from data, these systems relied on explicit knowledge encoded as rules. Their goal was to automate expert-level reasoning in areas where knowledge could be formalized clearly. The expert systems era developed primarily between the late 1960s and the 1980s. During this time, computing power increased, and organizations sought practical applications of AI. Researchers moved beyond theoretical demonstrations towards systems intended for operational use in medicine, science, and industry. Earlier symbolic AI programs solved puzzles or toy problems. Expert systems marked a shift towards solving real problems in specific professional domains. This transition required close collaboration with human experts and a focus on practical decision-making rather than abstract reasoning alone. The core idea behind expert systems was simple in principle: capture human expertise in a form a computer could use. If experts could explain how they reasoned, those explanations could be encoded as rules and applied consistently by a machine. Then general intelligence. It included facts, rules of thumb, heuristics, and decision criteria used by professionals. Expert systems did not aim to replicate human cognition broadly, only to perform well within narrow, well-defined problem areas. An expert system typically contained a knowledge base. This knowledge base stored facts about the domain and rules that described relationships between those facts. The quality of the system depended heavily on how complete, accurate, and current this knowledge representation was. The inference engine was the reasoning component of an expert system. It applied logical rules to the knowledge base to derive conclusions. The inference engine itself was generic, meaning it could be reused across domains if the knowledge base changed. A key design principle was separating knowledge from reasoning. Knowledge was encoded as rules and facts, while reasoning logic was handled by the inference engine. This modularity allowed systems to be updated or reused more easily than earlier monolithic programs. Most expert systems relied on if-then rules. These rules specified what action or conclusion should follow when certain conditions were met. The logic was explicit and deterministic, making system behavior predictable and traceable. Forward chaining was one common reasoning strategy. The system started with known facts and applied rules to infer new facts until a conclusion was reached. This approach worked well in monitoring or diagnostic tasks where data arrived incrementally. Backward chaining worked in the opposite direction. The system began with a hypothesis or goal and searched backward for evidence to support it. This approach was useful in diagnosis, where the system tested possible explanations against observed data. Many expert systems included explanation facilities. These allowed users to see which rules were applied and why a conclusion was reached. This transparency increased trust and made expert systems appealing in domains requiring accountability and justification. Several expert systems became well known. Dendril analyzed chemical compounds, while MySyn assisted in medical diagnosis. These systems demonstrated that machines could match or exceed expert performance in carefully constrained environments. MySyn focused on diagnosing bacterial infections and recommending antibiotics. It used hundreds of rules derived from medical experts. Although never deployed clinically, it performed at a level comparable to trained physicians in controlled evaluations. MySyn's success showed that explicit rules could capture expert reasoning effectively in narrow domains. Its accuracy highlighted the potential of AI when knowledge was stable, inputs were structured, and the problem space was well understood. Expert systems worked best in domains with clear boundaries. When problems were narrow, well-defined, and governed by established principles, rules could capture decision logic effectively. This alignment between problem structure and method was crucial to early success. Clearly defined problems reduced ambiguity. Inputs followed known formats, and outputs could be evaluated against accepted standards. This made it easier to encode expertise and verify system performance. Another success factor was access to human experts. Knowledge engineers worked closely with specialists to extract decision rules. When experts were available and cooperative, systems could be built with high-quality domain knowledge. Expert systems also benefited from predictable environments. When rules did not change frequently, systems remained valid longer. Stability reduced maintenance costs and made rule-based reasoning more reliable over time. Organizations began adopting expert systems in areas such as equipment configuration, credit evaluation, and diagnostics. These systems promised consistent decisions and reduced reliance on scarce expert labor. For businesses, expert systems offered several advantages. They standardized decision-making, reduced errors from fatigue or inconsistency, and allowed expertise to be reused across locations and shifts. Transparency was a major advantage. Because decisions were rule-based, organizations could inspect logic, audit outcomes, and explain results to stakeholders. This characteristic remains valuable today in regulated industries. Despite early success, limitations became apparent as systems grew larger. Rule sets expanded, interactions became complex, and maintaining consistency grew increasingly difficult. These issues challenged scalability. The knowledge engineering bottleneck emerged as a central problem. Extracting rules from experts was slow and expensive. Experts often struggled to articulate implicit knowledge, and translating it into formal rules required specialized skills. Updating systems proved difficult. As domains evolved, rules needed constant revision. Even small changes could require extensive rework, making expert systems fragile in dynamic environments. Expert systems were brittle. They performed well within their assumptions, but failed unexpectedly outside them. Unanticipated inputs or edge cases could lead to incorrect or nonsensical conclusions. Unlike modern learning systems, expert systems could not learn from experience. They relied entirely on predefined knowledge. Without manual updates, performance could not improve or adapt to new patterns. As rule counts increased, interactions between rules created combinatorial complexity. Reasoning became slower and harder to manage. This rule explosion limited how large and flexible systems could become. Handling uncertainty was another challenge. Early systems used ad hoc methods such as confidence scores, but these approaches were limited. Probabilistic reasoning was not yet mature enough to be integrated effectively. Expert systems depended heavily on human experts. Differences in expert opinion led to inconsistent rules. Subjectivity became embedded in systems, reducing reliability across contexts. Development costs were high. Building an expert system required years of collaboration, testing, and refinement. Many projects failed to deliver sufficient return on investment. Deploying expert systems in organizations was also challenging. Integrating them into workflows, training users, and maintaining trust required significant effort beyond technical development. Overpromising exacerbated disappointment. Some vendors and researchers claimed expert systems would generalize easily or replace professionals broadly. When this failed to materialize, confidence declined. As domains changed rapidly, static rule-based systems struggled to keep pace. This mismatch highlighted the limits of purely symbolic approaches in complex, evolving environments. By the late 1980s, enthusiasm for expert systems waned. Funding declined, projects were cancelled, and attention shifted elsewhere. This period contributed to what became known as an AI winter. The decline reflected unmet expectations rather than uselessness. Expert systems worked where assumptions held, but failed to scale broadly. The lesson was not that AI was impossible, but that intelligence was harder than anticipated. Expert systems taught valuable lessons about domain limits, knowledge representation, and system maintenance. These insights continue to inform modern AI design and deployment decisions. Many contributions endured. Rule engines, explanation methods, and structured reasoning remain relevant. Modern business rule systems inherit ideas from expert systems. Expert systems influenced modern AI by clarifying where explicit rules are useful and where learning is required. This distinction underpins today's hybrid approaches. Compared to machine learning, expert systems relied on rules rather than data. Machine learning addressed many scalability issues by learning patterns automatically, but sacrificed some transparency. Learning-based methods became necessary to handle scale, variability, and uncertainty. This shift marked a new phase in AI, building on but not replacing symbolic foundations. Expert systems were not a failure. They succeeded in narrow domains and demonstrated that parts of expertise could be formalized. Their limitations provided critical guidance for future approaches. A key lesson is to match methods to problems. Rule-based systems excel where rules are stable and explicit. Applying them outside such conditions leads to brittleness and disappointment. Expert systems still make sense in regulated or safety-critical domains with clear rules. Many organizations use hybrid systems combining rules and learning to balance reliability and flexibility. Hybrid approaches reflect continuity in AI history. New methods build on earlier insights rather than replacing them entirely. Understanding this continuity helps avoid repeating past mistakes. The expert systems era illustrates cycles of optimism and correction in AI. Each phase contributes knowledge, even when expectations must be revised. The core takeaway is that expert systems solved narrow, well-defined problems effectively, but struggled with scale and change. Their story explains both early AI success and subsequent caution. Studying this era provides perspective on modern AI claims. It reminds us to evaluate systems based on evidence, scope, and assumptions, rather than broad promises. Next, we will explore how limitations of expert systems motivated the rise of machine learning, marking a transition from rule-based intelligence to data-driven approaches that define modern AI. AI winters refer to periods when enthusiasm, funding, and institutional support for artificial intelligence declined sharply. These downturns followed waves of optimism that exceeded what technology could realistically deliver. Understanding AI winters helps explain why progress in AI has unfolded in cycles rather than along a smooth, linear path. The history of artificial intelligence is not a steady upward trajectory. Instead, it consists of repeated cycles of excitement, disappointment, and renewal. Each cycle reflects a gap between expectations and reality. AI winters emerged when promises outpaced practical results and confidence eroded. An AI winter is defined as a sustained period during which investment, research funding, and public interest in AI decline significantly. These periods are not caused by a lack of ideas, but by unmet expectations and a loss of institutional trust in AI's near-term potential. The term AI winter draws an analogy to economic winters, where activity slows and resources contract. In AI, winters occur when optimism freezes, projects are cancelled, and research becomes harder to sustain. The metaphor highlights both severity and temporary nature. Early AI researchers made ambitious claims. They predicted human-level intelligence within decades, and sometimes within years. These claims were often sincere, but underestimated the complexity of intelligence and overestimated available computing power, data, and algorithmic maturity. The gap between vision and reality became increasingly apparent. Early systems worked in constrained settings but failed in real-world environments. As limitations surfaced, confidence declined, especially among funding agencies and policymakers who expected broader impact. The first major AI winter occurred in the 1970s. After early enthusiasm in the 1950s and 1960s, progress slowed. Governments reduced funding when promised breakthroughs did not materialize, particularly in areas like language understanding and general reasoning. Funding cuts played a central role. AI research relied heavily on government support, and when confidence waned, budgets were redirected. Without stable funding, many research programs were scaled back or abandoned entirely. Technical limitations were significant. Computers were slow, Memory was expensive, and datasets were small. These constraints severely limited what AI systems could do, regardless of how clever the underlying ideas were. Symbolic AI systems depended on explicit rules and logic. While effective for structured problems, they struggled with ambiguity, noise, and real-world complexity. These weaknesses became increasingly visible as systems were tested beyond laboratory settings. A second AI winter occurred in the late 1980s and early 1990s. This period followed the rise of expert systems, which had initially appeared commercially promising, but ultimately proved difficult to scale and maintain. Expert systems required constant manual updates. As rules accumulated, systems became brittle and expensive to maintain. Organizations found that promised efficiency gains were offset by high operational costs. Commercial disappointment accelerated the downturn. Many companies invested heavily in AI products that failed to deliver expected returns. As a result, AI became associated with risk rather than opportunity. A major issue was overgeneralization. Narrow systems designed for specific tasks were marketed as broadly intelligent. When these systems failed outside their narrow domains, trust collapsed. Loss of trust was not limited to investors. Governments, corporations, and academic institutions grew skeptical. AI shifted from being seen as transformative to being viewed as unreliable and overhyped. Expectations played a decisive role. When timelines are unrealistic, even genuine progress can feel like failure. AI winters illustrate how managing expectations is as important as technical advancement. Media coverage amplified the problem. Sensational headlines created inflated expectations among the public and decision makers. When reality failed to match these narratives, backlash followed. Evaluation methods were also immature. Many systems lacked rigorous benchmarks, making it hard to assess real progress objectively. This made it easier for weak systems to be oversold. AI research ecosystems were fragile. Heavy dependence on short-term funding made them vulnerable to shifts in political and economic priorities. When funding dried up, entire research areas stalled. Tension existed between academic goals and industry expectations. Researchers explored long-term questions, while funders wanted immediate applications. This mismatch intensified disappointment. AI winters revealed fundamental truths about intelligence. Human cognition involves context, learning, embodiment, and adaptation, qualities far harder to engineer than early researchers anticipated. One key lesson was that intelligence is not monolithic. Narrow competence does not equal general intelligence. Confusing the two contributed heavily to unrealistic projections. Another lesson involved data. Early AI lacked sufficient data to learn from experience. Without large, diverse datasets, systems could not generalize effectively. Compute limitations also mattered. Many algorithms that work today were theoretically known decades ago, but were impractical without modern hardware. Compute limitations also mattered. Many algorithms that work today were theoretically known decades ago, but were impractical without modern hardware. Machine learning represented a shift from hand-coded rules to data-driven learning. This transition addressed many scalability problems that symbolic systems could not solve. Statistical thinking allowed systems to handle uncertainty more naturally. Probabilistic models replaced brittle logic, improving robustness in real-world settings. Infrastructure improvements were critical. The rise of the internet, digital storage, and distributed computing changed what was feasible for AI research and deployment. Infrastructure improvements were critical. The rise of the internet, digital storage, and distributed computing changed what was feasible for AI research and deployment. Commercial alignment also improved. AI began solving clearly defined problems with measurable value, such as search, recommendation, and pattern recognition. Today's AI boom rests on stronger foundations. Data abundance, scalable compute, and algorithmic maturity reduce, but do not eliminate, the risk of another winter. However, hype has not disappeared. Overclaims still occur, especially around general intelligence and autonomy. Awareness of AI winters helps contextualize these narratives. Avoiding another AI winter requires responsible communication. Claims must align with evidence, and limitations must be acknowledged openly. Governance plays a role. Stable funding, long-term research support, and realistic policy expectations help prevent boom and bust cycles. Research discipline matters. Clear benchmarks, transparent evaluation, and peer review reduce the risk of inflated claims dominating public discourse. AI winters should not be seen as failures, but as corrections. They reset expectations and redirect effort toward more sustainable paths. Historical awareness is valuable. Understanding past cycles helps researchers, investors, and policymakers avoid repeating the same mistakes. The key takeaway is balance. Progress requires ambition, but also humility. AI advances when claims are grounded and development is incremental. For policymakers, AI winters highlight the importance of stable, long-term investment rather than reactionary funding decisions. For practitioners, the lesson is honesty. Deploy systems for what they can reliably do, not what marketing suggests they might do someday. For the public, AI literacy helps distinguish real capability from speculation. Informed skepticism supports healthier technological adoption. AI winters remind us that progress is uneven. Breakthroughs, often, each winter contributed knowledge. Failures clarified limits, refined methods, and shaped future research directions. Rather than erasing value, winters filtered unrealistic approaches. Understanding AI winters encourages patience. Complex systems require time, iteration, and learning from mistakes. Modern AI benefits from these lessons. Today's systems are evaluated more rigorously and deployed more cautiously. Still, vigilance is necessary. The same forces that caused past winters, hype, overpromise, misalignment, can reappear. History does not repeat exactly, but it often rhymes. Awareness helps guide responsible innovation. AI winters show that setbacks are part of progress. What matters is how systems, institutions, and societies learn from them. Next, we move from historical cycles to modern machine learning, examining how data-driven approaches transform AI and why today's systems differ fundamentally from those of the past. The rise of machine learning marked a fundamental turning point in artificial intelligence. Instead of relying on hand-coded rules, researchers began developing systems that could learn behavior from data. This shift addressed key limitations of earlier approaches and opened the path toward more adaptable and scalable AI systems. Symbolic AI struggled as problems grew more complex. Rule-based systems became fragile, expensive to maintain, and difficult to scale. Each new scenario required additional rules, creating tangled logic structures that were hard to debug and impossible to generalize beyond narrow environments. Real-world environments contain ambiguity, noise, and variability. Capturing this complexity using explicit rules proved unrealistic. The growing mismatch between rigid symbolic systems and messy reality pushed researchers to explore alternatives that could cope with uncertainty more naturally. One major obstacle was the knowledge engineering bottleneck. Extracting expertise from humans and translating it into formal rules was slow, costly, and error-prone. Many experts could not fully articulate how they made decisions, limiting what could be encoded. This frustration led to a critical question. Instead of programming intelligence directly, could machines learn behavior automatically? Rather than telling systems what to do, researchers explored ways for systems to infer patterns from examples and data. Early statistical approaches provided a foundation. Probability theory and statistics offered tools for reasoning under uncertainty. These methods allowed systems to work with likelihoods instead of absolute truths, better reflecting real-world conditions. The philosophical shift was profound. AI moved away from logic-heavy certainty toward probabilistic reasoning. Intelligence was reframed as pattern detection and optimization rather than symbolic manipulation alone. Machine learning formalized this idea. A machine learning system improves its performance on a task through experience, typically by adjusting internal parameters based on observed data rather than explicit instructions. At its core, machine learning replaces rules with examples. Instead of encoding every decision path, developers provide data illustrating correct behavior. The system discovers patterns that approximate the desired mapping. Data became the primary input. Historical records, measurements, user interactions, and observations all served as raw material. Learning systems extract statistical regularities from this information. This represented a new programming paradigm. Developers defined learning objectives and architectures, but behavior emerged during training. Systems were shaped indirectly rather than specified line by line. Machine learning relies heavily on mathematics. Linear algebra supports vectorized representations, calculus enables optimization, and probability theory manages uncertainty. These tools replaced symbolic logic as the dominant technical foundation. Models function as mathematical mappings from inputs to outputs. Parameters determine how inputs are transformed. Learning adjusts these parameters to reduce error on observed examples. Supervised learning became a dominant paradigm. Systems learned from labeled examples where correct outputs were known. This approach proved effective for prediction, classification, and regression tasks. Unsupervised learning addressed a different challenge. Without labels, systems sought structure in data, identifying clusters, patterns, or latent features. This enabled discovery rather than prediction. Reinforcement learning introduced feedback-based learning. Systems learned through trial and error, guided by reward signals. This approach mirrored certain aspects of behavioral learning. Datasets became central assets. The size, diversity, and quality of data directly influenced performance. Data collection, storage, and management emerged as strategic priorities. Data replaced handcrafted rules. Behavioral knowledge was embedded implicitly in examples rather than explicitly written logic. This reduced manual engineering, but increased dependence on data quality. A key goal of machine learning is generalization. Models must perform well on unseen data, not just memorize training examples. This distinguishes learning from simple lookup. Loss functions quantify mistakes. Optimization algorithms iteratively adjust parameters to minimize these losses. Learning becomes a mathematical process guided by error reduction. Probabilistic outputs allow systems to express uncertainty. Predictions are not absolute statements but likelihoods, enabling more nuanced decision-making. Machine learning systems tolerate noise better than rule-based systems. Imperfect data does not necessarily break behavior, making learning systems more robust in real environments. Compared to expert systems, machine learning scales more effectively. Adding data often improves performance without rewriting logic, enabling broader deployment. However, trade-offs emerged. Learned models are often less interpretable. Understanding why a system made a decision became harder than tracing rule-based logic. Early applications demonstrated value. Spam filters adapted to new messages, handwriting recognition, improved accuracy, and search engines became more relevant. Industry adoption followed gradually. Companies recognized that learning systems improved with usage, creating incentives to deploy and iterate continuously. A data-centric mindset emerged. Organizations began treating data as a strategic resource. Better data meant better models, reinforcing investment cycles. Infrastructure evolved to support learning. Storage systems, distributed computing, and cloud platforms enabled handling massive data sets efficiently. New professional roles appeared. Data scientists, machine learning engineers, and ML ops specialists became essential to AI development pipelines. Evaluation became critical. Performance metrics and benchmarks replaced anecdotal success claims, grounding progress in empirical measurement. Overfitting emerged as a central risk. Models could memorize training data while failing on new inputs. Validation techniques were developed to mitigate this. Bias entered systems through data. Learning reflects historical patterns, including societal inequalities. This challenged assumptions of neutrality. Machine learning does not imply understanding. Models detect correlations, not meaning. Outputs may appear intelligent without semantic comprehension. Despite advances, machine learning systems remain narrow. Each model is optimized for a specific task with defined objectives. The gap between machine learning and general intelligence remains large. Learning systems do not transfer knowledge broadly without redesign. Machine learning succeeded because it automated knowledge acquisition. Instead of encoding expertise manually, systems inferred behavior statistically. Feedback loops accelerated progress. More usage generated more data, which improved models, which attracted more usage. This shift laid the groundwork for deep learning. Data-driven methods, optimization techniques, and evaluation culture made later breakthroughs possible. Research culture changed. Progress was measured by benchmarks, data sets, and reproducible results rather than theoretical elegance alone. Industry strategy shifted toward experimentation. Models were deployed, monitored, and refined continuously rather than finalized up front. New failure modes emerged. Errors could propagate silently at scale, requiring new forms of monitoring and governance. Accountability became complex. Responsibility for decisions was harder to trace when behavior emerged from data rather than explicit rules. Machine learning redefined practical AI. It enabled widespread deployment and measurable value across many domains. The symbolic era did not disappear entirely. Rule-based methods remain useful where logic is stable and explicit. The key lesson was alignment. Methods must match problem structure. Learning excels where data is abundant and environments vary. Machine learning represents continuity, not replacement. It built on earlier AI insights while addressing their limitations. Historically, this shift marked the end of symbolic dominance and the beginning of modern AI practice. Understanding this transition helps contextualize current AI capabilities without exaggeration or dismissal. The rise of machine learning explains why AI finally scaled beyond laboratories into everyday systems. Next, we will examine how deep learning transformed machine learning further, enabling breakthroughs that reshaped vision, speech, and perception. The deep learning revolution marks a major turning point in artificial intelligence history. Rather than introducing a completely new goal, deep learning transformed how learning systems are built and scaled. This video explains why deep learning succeeded where earlier approaches struggled. The objectives of AI did not change. Systems still aim to recognize patterns, make predictions, and support decisions. What changed were the methods, the scale of computation, and the availability of data, enabling far more complex models to be trained effectively. Early machine learning systems relied heavily on human-designed features. Engineers manually specified what aspects of data mattered, limiting flexibility and performance. These systems worked well in constrained settings, but struggled with feature engineering became a bottleneck. Extracting useful signals required deep domain knowledge and extensive experimentation. As problems grew more complex, it became increasingly difficult for humans to anticipate all relevant patterns in advance. Real-world data introduced complexity that exceeded what shallow models could handle. Images, speech, and language contained layered structure that simple representations could not capture effectively. This mismatch limited progress using earlier techniques. Neural networks offered a potential solution, but they were not new. Early versions existed decades earlier, yet they failed to scale due to limited data, insufficient computing power, and unstable training methods. From the 1950s through the 1980s, neural networks attracted periodic interest. However, practical applications were rare, and performance gains were inconsistent. As a result, neural networks were often set aside in favor of symbolic or statistical approaches. The failure of early neural networks was not conceptual but practical. Training deep models was slow, unstable, and computationally expensive. Without large datasets and efficient hardware, their theoretical advantages could not be realized. By the early 2000s, conditions began to change. Digital data volumes increased rapidly, computing hardware improved, and optimization techniques matured. These factors collectively enabled neural networks to be revisited under far more favorable conditions. Deep learning refers to neural networks with many layers. Each layer transforms data into increasingly abstract representations, allowing systems to learn hierarchical structure directly from raw inputs, rather than relying on handcrafted features. Depth allows models to represent complex relationships. Early layers capture simple patterns, while later layers combine them into more meaningful structures. This hierarchical learning mirrors how many real-world signals are organized. A key advantage of deep learning is representation learning. Instead of engineers defining features manually, models learn representations automatically from data, reducing reliance on human intuition and increasing adaptability. For example, image models learn edges, shapes, and objects directly from pixels. Speech models learn phonemes and words from sound waves. This ability to learn directly from raw data marked a significant departure from earlier methods. Neural networks consist of input layers, hidden layers, and output layers. Information flows through these layers, with each transformation guided by learned parameters adjusted during training. The term deep refers to the number of layers. More layers allow more expressive models, capable of capturing complex nonlinear relationships that shallow systems cannot represent effectively. Deep learning also depends on large data sets. Learning robust representations requires exposure to diverse examples. As data availability increased, deep models gained the opportunity to generalize better. The rise of the internet, digital sensors, and large-scale logging created unprecedented amounts of data. This data provided the raw material necessary for training deep neural networks effectively. At the same time, graphical processing units, or GPUs, became essential. Originally designed for graphics, GPUs excel at parallel numerical computation, making them well-suited for neural network training. Neural networks rely heavily on matrix operations. GPUs perform these operations far more efficiently than traditional processors, dramatically reducing training time for large models. As models grew larger, infrastructure evolved alongside them. Hardware, software frameworks, and cloud platforms co-developed, enabling deep learning systems to scale rapidly. A pivotal moment occurred with the ImageNet competition. Deep learning models dramatically outperformed previous approaches in image recognition, drawing widespread attention from academia and industry. These results demonstrated that deep learning could achieve substantial accuracy gains when trained at scale. This success validated years of research and shifted the direction of AI development. Computer vision was transformed. Tasks such as object detection, image classification, and segmentation became far more accurate, enabling real-world applications previously considered impractical. Speech recognition also improved significantly. End-to-end deep learning models replaced complex pipelines, achieving higher accuracy and robustness across diverse accents and environments. Natural language processing benefited as well. Models learned richer representations of text, improving translation, summarization, and question-answering capabilities. Deep learning reduced reliance on handcrafted features across domains. A single model architecture could often be adapted to multiple tasks, increasing efficiency and reusability. Scaling became a central principle. Larger models trained on more data consistently achieved better performance, leading to systematic exploration of scale as a driver of progress. Researchers observed predictable improvements as models grew. These empirical patterns reinforced the idea that continued scaling could unlock further capabilities. As a result, AI research increasingly resembled engineering. Optimizing infrastructure, data pipelines, and training efficiency became as important as algorithmic innovation. Industry adoption accelerated rapidly. Technology companies invested heavily in deep learning, integrating it into products and services at global scale. Search engines, recommendation systems, translation tools, and voice assistants all began relying heavily on deep learning models to improve performance. Research culture shifted toward benchmarks and competitions. Progress was measured quantitatively, reinforcing empirical evaluation over theoretical elegance alone. New risks emerged alongside success. Deep learning models are often opaque, making it difficult to understand or explain individual decisions. Interpretability challenges complicate trust, accountability, and debugging. Even experts may struggle to diagnose why a model behaves as it does. Training large models is resource-intensive. Energy consumption, financial cost, and environmental impact became growing concerns. Deep learning systems are highly data-dependent. Biases in training data can be amplified, affecting system behavior across populations. High performance can mask weaknesses. Models may fail in unexpected ways when encountering conditions outside their training distribution. Despite impressive results, deep learning systems do not understand meaning. They learn statistical patterns, not concepts or intentions. Capabilities remain narrow. Models excel at specific tasks but struggle to generalize beyond their training context. Nevertheless, deep learning matters because it delivered sustained, measurable progress. It moved AI from promise to widespread practical deployment. Deep learning now forms the foundation of modern AI systems. It enables architectures that support large-scale learning and representation. Crucially, deep learning made generative models feasible. High-capacity representations allowed systems not only to recognize patterns, but also to generate new content. This shift expanded AI from perception tasks into creative and generative domains, setting the stage for the next phase of AI history. Historically, deep learning marks a transition from shallow, task-specific models to scalable, general-purpose learning frameworks. The key lessons are clear. Data scale matters, compute matters, and model capacity matters when aligned with the right infrastructure. At the same time, limits persist. Deep learning remains brittle, resource-intensive, and dependent on human-defined objectives. Deep learning should be understood as a powerful tool, not a complete solution to intelligence. Its historical significance lies in changing expectations. Progress became continuous rather than episodic. This sustained progress explains why deep learning endured where earlier AI approaches stalled. Next, we examine the generative AI era, where deep learning techniques underpin systems that create text, images, and other content, marking another major shift in artificial intelligence. The generative AI era represents a new phase in the history of artificial intelligence. Rather than focusing solely on prediction or classification, AI systems now generate text, images, code, and other content. This shift reflects deeper changes in architecture, scale, and deployment. Earlier AI systems primarily recognized patterns or selected predefined outputs. Generative AI systems go further by producing novel content. This does not mean creativity in a human sense, but statistical generation based on learned patterns from large data sets. Generative AI refers to models that learn the underlying structure of data and sample from it to create new outputs. These outputs are not retrieved from a database, but synthesized dynamically, making each response potentially unique. Historically, most AI applications were reactive. They responded to inputs by selecting labels or scores. Generative systems instead construct outputs token by token, enabling flexible responses across many contexts. What distinguishes this era is not a single invention, but a convergence of factors. Architecture, data scale, and infrastructure aligned in a way that enabled generative models to perform reliably at scale. Deep learning provided the foundation. Neural networks capable of learning high-dimensional representations made it possible to model complex data distributions across text, images, and audio. The transformer architecture was a turning point. Unlike earlier sequence models, transformers process inputs in parallel and rely on attention mechanisms to model relationships efficiently. Transformers use attention to determine which parts of an input are most relevant when generating each output element. This design enables efficient handling of long sequences and complex dependencies. Attention allows models to dynamically focus on context. Rather than processing information sequentially, transformers evaluate relationships across the entire input at once. This efficiency made it feasible to train very large models. Longer context windows and richer representations became practical, improving coherence and relevance in generated outputs. Language played a central role in this shift. Text data is abundant, diverse, and expressive, making it an ideal training medium for large generative models. Large language models emerged by scaling both data and parameters. Increasing model size consistently improved performance across a wide range of tasks. Model parameters represent learned relationships. As parameter counts grew, models gained greater expressive capacity, allowing them to capture more nuanced patterns in data. Pre-training became the dominant paradigm. Models learn general language patterns through self-supervised objectives before being adapted to specific tasks. Fine-tuning allows pre-trained models to specialize. This separation enables reuse of general knowledge while adapting behavior for particular applications. Generative models became general-purpose tools. A single model could perform translation, summarization, question answering, and more without task-specific redesign. Generative AI expanded beyond text. Models now generate images, audio, video, and code using similar underlying principles. Multimodal systems integrate multiple data types within a single model. This enables richer interactions and broader applicability across domains. Importantly, generative AI produces new content rather than retrieving stored examples. Outputs are statistical constructions based on training data distributions. Despite impressive outputs, generative models do not understand meaning. They generate based on patterns, not intent, awareness, or reasoning. Outputs often appear intelligent because they are fluent and contextually appropriate. This fluency can be mistaken for understanding. Natural language interfaces lowered barriers to use. People can interact with AI systems conversationally without technical expertise. This shift changed user experience. AI systems began to feel more like assistants than tools, increasing adoption and experimentation. Public exposure to AI expanded rapidly. Generative systems reached mainstream users, unlike earlier AI technologies that remained largely invisible. Access to generative AI became widespread. Cloud platforms and APIs enabled organizations and individuals to integrate AI into workflows quickly. Economically, generative AI supports productivity. It assists with drafting, coding, summarizing, and analysis rather than replacing entire roles outright. Industries such as media, education, and software development experienced rapid experimentation. Generative tools altered how content and code are produced. The speed of adoption exceeded prior AI waves. Network effects and ease of integration accelerated diffusion across sectors. Cloud infrastructure enabled this scale. Centralized compute and standardized interfaces allowed models to be deployed globally. AI increasingly functions as a platform service. Models are embedded into applications rather than delivered as standalone products. New risks accompany these capabilities. Generative systems can produce incorrect information confidently, creating challenges for trust and reliability. Because outputs appear authoritative, users may over-rely on them. Managing uncertainty and error becomes essential. Biases present in training data can be reflected and amplified in outputs. This raises fairness and representation concerns at scale. Generative AI also raises intellectual property questions. Training data sources and output ownership remain contested. Training large models is resource-intensive. Energy use and cost create sustainability and access challenges. Control over advanced models is concentrated among organizations with significant resources. This raises questions about power and governance. Regulatory frameworks struggle to keep pace. Deployment often outpaces oversight, creating gaps in accountability. Public discussion sometimes conflates generative AI with general intelligence. This confusion fuels unrealistic expectations and fear. Generative AI remains narrow. It performs tasks within learned domains and lacks autonomy or general reasoning. Media attention amplified this wave. Visible outputs and conversational interfaces made AI feel suddenly present. Structurally, This era differs from earlier AI cycles. Progress is continuous, driven by scaling rather than isolated breakthroughs. Unlike past waves, generative AI delivers sustained value across many domains, supporting long-term adoption. Its endurance reflects real utility. Organizations continue investing because benefits are measurable and repeatable. Generative AI is becoming infrastructure. It is embedded into everyday tools and workflows. Long-term implications extend to work, education, and knowledge production. These changes will unfold gradually rather than instantly. Generative AI functions as a general-purpose technology, affecting many industries simultaneously. Despite its impact, limits remain. These systems lack understanding, agency, and intent. History reminds us that expectations must be managed. Capability does not equal intelligence. This era completes the historical arc from symbolic rules to data-driven generation. Next, we move from history to foundations by examining core AI concepts that explain how these systems actually work.